Hello, everyone. This is Christine Perey, chair of the AR for Enterprise Alliance Research Committee. Today we have an exciting, very fast-moving subject, how to use 3D Gaussian splatting for AR-related tasks, functions, and features. I'm very excited to have Nikhil Keetha today with us. As you can see on the screen, he's one of a group of researchers who's working on these topics. So very, very prestigious institutions, Carnegie Mellon University, MIT. There are people who have since dispersed from those institutions, and they are working in industry as well as in other research faculty, laboratories. I also want to say that while there's a group of people who worked on this particular study that we're going to hear about today, this topic of 3D Gaussian splatting is huge in the research world, and it's also making its way into commercial world. I think it was just this week that Niantic announced it was going to open source an application that uses 3D Gaussian. I believe that we are at the cusp of something big, bigger than we've seen in a while for tracking, and at least. And I'm very, very pleased to be able to host today's webinar. Thank you, Nikhil, for agreeing to join us and sharing your knowledge and helping our community to better understand the benefits and some of the trade-offs that are being made in these new techniques. I'm going to turn it over to you. Let's listen to this exciting topic.
Thank you so much for the invite, Christine. And yeah, hey everyone, I'm Nikhil. I'm a PhD student at CMU, and I'll be giving this talk today. I guess my goal for this talk today is really to introduce the world of 3D Gaussian splatting, as Christine mentioned, has been really blowing up the past year, and then also give you a perspective into how this can be useful for AR applications, which you guys are interested in. So yeah, let's probably get started then. So today I'll be presenting SplaTAM, an approach to both track and map the scene. So in terms of tracking, you'd basically be tracking the camera and also be reconstructing the scene so that you can get this high-fidelity map, which I'm showing on the right side here. So you might be wondering what's the secret to achieve this, right? So that's my agenda for the talk today. By the end of this talk, I'll convince you that these 3D Gaussians are blobs, are the right representation to actually do dense lam. So I think to get started, I think we first need to understand why we need 3D Gaussians in the first place. And then to this talk, I kind of motivate this, and then this will be a story of the talk in some sense. And then, yeah, firstly, let's first start by diving into the world of reconstruction and then a SLAM to kind of understand the current state of space, eventually. So a typical way of how people reconstruct or I would say perform SLAM right now is basically to run like structure from motion, where you try to both figure out your camera motion and you also try to get the geometry. And once this is done, you kind of have a lot of these established tools in the current world, where, like, for example, radiance fields and etc., which help you get like these high-fidelity reconstructions. However, the problem is most of these things assume an offline setup and require a lot of time, maybe even several days, and this is really a luxury. And then when you consider applications like robotics or augmented reality, you don't really have the luxury of time. And then we need to actually reconstruct these things online and in a fast way. So then how can we actually do this? So the answer is simultaneous localization and mapping, where the goal is really to both locate yourself and also to map your environment with high fidelity. But then I would say SLAM is like a kind of a chicken and egg problem, where you actually need a map for localization and you need a location to build a map. So you actually have to build the map at the same time and also estimate your pose, which is a kind of a hard problem in some sense. And then this is a very well-established field in general. I think for the past few decades, people have been making progress towards this problem. And then there are a few key factors which kind of influence the performance of these methods. So the first one basically is how you kind of keep track of information. Do you do this in a sparse way, for example, where you just have like unique features in the scene, or do you do this in a dense way where you actually use all the 3D geometry available? Then the other one is like, how do you update the map? So now, for example, let's say when you're looking at new information, or like when a person is moving to a new room, you also have to map all of this new content. So then how easily can you actually do this? Then the other thing is fidelity. So like, is this reconstruction actually high in terms of fidelity? For example, like in AR, you'd probably want the pass through and also the content which you're showing to have the same kind of resolution and the consistency in terms of lighting. So yeah, so now since we've really established the key factors which we need, how you kind of represent the scene is a very important factor which impacts all of these things. And currently, the way this is typically done is there's basically two types of representations. Where the first one are these like explicit representations. I would say the one of these, like most of these, date back to a few decades. For example, points, circles, meshes, and all these kind of things. Well, then how well do these representations actually do? So typically, when you use these representations, people tend to register them using methods like ICP. However, this kind of doesn't necessarily use all the information available. You kind of have to sparsely select in interest of time. And also, it's kind of because of this problem, they kind of tend to struggle with like textureless regions. For example, over here in the table, you can see it kind of creates a duplicate copy of this table. And secondly, the fidelity is kind of limited with these classical representations. But lastly, because this is like a very well-established set of representations, there's a lot of research and technological progress here where people have tried to get these things to work very fast. I would say more recently, there has been a gaining of popularity with radiance fields. And you can basically think of radiance fields as a fuzzy way of representing the world, where you first start with like this fuzzy volume, and then as you train this network, you kind of get geometry and all of this stuff. And then I would say the key technique to kind of achieve this in a nerve basically is you kind of pass rays through a volume, and you try to like query this network along these rays to get like the properties of the volume, for example, the color, the opacity, and all the different things. And then you kind of take multiple images and you train this representation on the fly. And then people have also used the same thing in an online setup. So for example, over here, they're fitting a network basically to do SLAM in some sense. And then, so how do these actually work when you apply them to real world problems? Since using these rays is a expensive process, generally nerves have like nerve-based SLAM methods have to sparsely select what information is useful for tracking. And again, here you're kind of trading off information density for speed. Then likewise for map update, because you have like this neural network kind of representing the scene, it tends to interpolate things which you haven't observed before. So it's kind of hard to determine what is new and what is not new, essentially. So it didn't necessarily elegantly come out. But I guess one of the real cool benefits of this representation is that it has really high fidelity, both in terms of geometry and photorealism, which is nice for both VR and AR applications. Given this landscape, we were really excited when 3D Gaussian Splatting came out last year, kind of showing that it could actually empower all of these factors without any kind of trade-off, which was really cool. So in this talk, I'll kind of show you how 3D Gaussians enable all of these key factors. So yeah, again, let's consider the table which we've been looking at so far. The first step basically is that, I'll kind of describe this in more detail later. But then the nice properties of 3D Gaussian splatting is that it actually is very fast. And then you also get this benefit of doing dense optimization, which can be used in a SLAM setup. Likewise, again, coming back to the map update scenario, the cool thing with Gaussians is that they can actually tell you elegantly what is missing in a scene, just given the properties of these representations, basically. And then finally, not just our paper, but then a lot of other papers also in this space across the past 1 year have really showed that 3D Gaussians can actually enable very high fidelity reconstruction. So, for example, these are some pass-throughs which people have connected with common apps like nerve capture. So then I guess how do 3D Gaussians actually achieve all of these nice properties? So before we dive into the world of 3D Gaussian splatting, I think we first need to understand a bit about rasterization, which is a classical graphics technique. So in rasterization, how things mainly work is given these three triangles, you would then, and let's say you have some camera pose and you want to render these triangles, you would assign the pixel values based on the depth. So for example, you first take the red triangle and you assign the values, and because the green one is in front of the red one, you kind of overwrite the values. Likewise, since the blue one is behind these two triangles, when you actually render the blue triangle, what you'll see shortly is that the values don't get overwritten. So only new values are kind of added essentially. So this, I would say, basically the trick essentially is just to project all of these 3D representations to a 2D image plane, and then just assign colors based on the depth. And then so given this background with rasterization, I think now we are actually ready to understand what 3D Gaussian splatting is. So so this is the original 3D Gaussian splatting paper, which came out in last year August. And then the way this method basically works is you first have some kind of method like call map, where you run where you get like some sparse geometry of the scene and also some camera poses. Then you first initialize all of these points to 3D Gaussians. So you might be wondering what a 3D Gaussian actually is. So you can basically think of a 3D Gaussian as just kind of representing the influence of a Gaussian on a 3D point. And then in the original paper, they kind of represent a 3D Gaussian with all of these parameters, where basically you have its position in 3D, its scale, rotation, opacity, and you also have all of these color and other properties basically. So now, given these 3D Gaussians, and now let's say given some camera pose, you can then render these Gaussians to a 2D image plane, basically, using this equation, which is, and then it was basically just like a single matrix multiplication, so it's like insanely fast to do. And then basically, for example, let's say you had some 3D Gaussians, and then when you project it, you kind of end up with these 2D Gaussians in the screen space, which is actually what you would look at on your computer screen or like when you're actually looking at these renderings, basically. So once you have these 2D Gaussians on the image plane, how this method basically works is, if you recall, we were doing rasterization, right? So now they use a fancy version of this rasterization, basically, where you kind of divide the screen into 16 by 16 tiles, and you sort the Gaussians for each tile by depth, and then you can then assign the color for each pixel, basically, given by this equation. And then likewise, you can also get the depth of the pixel, and then also the opacity, as in, like, for example, do you actually see any kind of volume along this pixel or not? And then 3DGS basically implements all of this in optimized CUDA kernels. So this actually runs very fast on GPU because of the ability to parallelize all of these things on the GPU. And then if we actually take a closer look at the alpha compositing, now given these depth-sorted Gaussians, and then given this Gaussian function, basically, you can basically compute this thing called a mask, which basically tells you what is occupied and what is not occupied. So for example, let's say along the pixels along which you have projected Gaussians, you'll actually have some values here. While, for example, in empty space, because you have no Gaussians projecting to these pixels, it's all white, as in, like, it's just zero values. Like, you won't really get any kind of accumulated opacity here. And then likewise, you can also get, and I guess this is the equation of how you kind of do that. You loop over all of these 2D Gaussians. You take the influence of the current 2D Gaussian, and then you have this thing to compute the transmittance to the Gaussian, and then you can basically sum all of these things until you reach a maximum value of 1 along the pixel, because, like, 1 is basically, you've seen everything you can see along that direction, essentially. And then likewise, you can also get the depth in a similar fashion. So because you have, like, let's say you have multiple Gaussians and you know the depth of all those different Gaussians, you can also get the cumulative depth rendering essentially. And likewise, you can also get color, because like each Gaussian has a color to it. So now when you're doing this rendering, you can also multiply the color of each Gaussian in this process, and then now you can actually get a rendered image basically. So now, given this entire machinery, how you kind of update this representation basically is you have some set of ground truth images, basically the images which you've captured, and now you have this 3D Gaussian based representation. So you basically render this representation to get some initial rendering. You compare this with your original images, where basically you're just comparing each pixel and kind of getting an error. And then now you just use this to update the Gaussian representation basically iteratively, by minimizing this loss essentially. So yeah, so now coming back to our agenda slide, we can now see that 3D Gaussians clearly empower all of these three different factors which are necessary for a SLAM system, which has to both track the camera and also map the scene. So then I guess now you might be wondering, I guess like now I've just kind of showed you the nice properties of 3D Gaussians, but how do you actually use them to do SLAM? So you basically use these three simple steps, that is silhouette guided camera tracking, and also silhouette guided map densification, and also a very simple multi-view map optimization to kind of achieve this. And I'll kind of give you an intuitive sense of how this happens. So yeah, so given a 3D Gaussian map at time step t-1, we can use the concept of 3D Gaussian splatting to basically render this map from given camera pose. For example, in the AR world, you can think of this as like your current head pose in some sense. And then you can actually get this render GT-1 and ET-1. And I guess one of the key differences from the original paper is that we actually use a lot more lesser parameters to kind of for better efficiency. And then for the first frame, what we basically do is because we have RGB-D information, we first back project this RGB-D into a point cloud, and then similar to the original paper, we just initialize the point cloud as the Gaussian map. So and then which is fairly easy to do with this equation on the bottom. So now, given this Gaussian map, and then let's say we now have, let's say, for example, the person is moving his head around, and now you have a new frame. You basically want to now track the new frame. Basically, you basically want to estimate the camera pose for this new frame which you're seeing. So how you basically do this? You first start by optimizing the camera, and then as the camera starts to change, as shown on the right side, you'll have newer renderings, and then you compare this to the original, like I guess the current image which you're actually seeing. But the problem is basically here, if you naively do this, the problem is you obviously have like new data which you can, like I guess new parts of the map which you haven't seen before. And then if you use this for the optimization, this can be super noisy. So to mitigate this, what we basically do is we actually use the silhouette. That is actually the opacity, or like I guess the mask kind of indicating if there's Gaussians along this pixel essentially, to tell us if there's empty space or non-empty space. And now we can actually weight this optimization with this silhouette, and this elegantly kind of helps us track to the correct camera pose. So for example, over here, you can see how like we can use the silhouette-based loss masking to actually guide us to the right camera pose. So this is like a high-level overview of how we do frame-to-frame camera tracking. So I guess once you've kind of done frame-to-frame camera tracking, you also want to ideally add all of this new information which you've seen. So if you recall, like the silhouette mask kind of tells you directly what is kind of new, and then what is empty space, like what is empty space and what is occupied space in some sense. So now with this information, you can actually just take the newer frames depth, and you can actually compute the color and depth points which you have to add to the current frame essentially, which is shown on the right side essentially. And now you can actually add these new Gaussians to the map. For example, over here we show them in red on the right side image. And then again, similar to the trick I showed you before, I mean, basically you can quickly figure out what the size of these Gaussians should be based on their depth and the focal length of the camera. So that's basically the Gaussian densification for SLAM. Observation for SLAM. Put these new Gaussians into the scene, they're not going to look very good. You probably won't optimize them. So what we basically do is we select a few frames from the past sequence, and you basically use all of these frames together and then do the typical 3D Gaussian splatting where you just optimize the 3D Gaussians to kind of improve the color fidelity and also the geometric fidelity of the representation. So this process happens in an online fashion where, for example, you have a Gaussian map and you have an incoming frame. You first start by camera tracking. Then you do Gaussian densification. That is basically you add new content to the map. And then you also update the map to kind of improve the fidelity of the map. And all of this together enables you to do SLAM, which is basically online camera tracking and reconstruction. Okay, so I guess I've kind of showed you with that these three simple tricks. You can enable SLAM with 3D Gaussians. But then obviously, I guess SLAM is a very developed field, and you already have lots of other methods available in the space. So I guess one question you might be wondering about is, how well do these Gaussian representations actually perform compared to the older ones in some sense? So before we dive into the results, let's quickly just take a quick overview of what the metrics are in this space. So I would say in the SLAM space, the main metric basically is this thing called average absolute trajectory error, also called ATE. We basically compute the root mean squared error between the ground truth and the estimated pose after performing some alignment on the trajectories. On the other hand, in terms of I would say the view synthesis world, which is more like aligned towards like AR and VR applications, you really care about the fidelity of the images. So these are like three different metrics which are kind of used in this space, which is basically PSNR, SSIM, and then LPIPs, where typically higher PSNR and SSIM are good scores, while lower LPIPs is a better score. And likewise for SLAM, a lower RMSE is a better score essentially. And then in terms of data sets, typically people use three standard benchmark data sets for SLAM, where the first one is Replica, which is a synthetic data set, while ScanNet and TUM RGB-D are calculated using like RGB-D sensors. And I guess one of the limitations with prior benchmarks is that generally in I guess like when you want to really compare the fidelity of your representations, you want to kind of also have held out images from camera views which you actually haven't used for the reconstruction, which is basically this whole thing of novel view synthesis testing, where novel just means like it's a camera pose which you haven't really observed when you're building the reconstruction. And then in the world of like radiance fields, and I would say like the latest 3D Gaussians, NVS benchmarking actually is a very critical thing to do. And we were surprised that SLAM in the SLAM world was not a norm. So we actually repurposed another novel view synthesis datasets called ScanNet++ for the purpose of SLAM, and we actually use this in our work to compare the different methods available. And then lastly, I guess before we actually get into the results, the last thing I want to kind of introduce are basically the baselines, or like I would say like the prior state of the art, or like existing methods which people in this space tend to use for like camera tracking and scene reconstruction. So the first one basically is this thing called NiceLam, where the idea is basically just to use multiple sets of tiny nerves, where I kind of introduce nerves in the starting of the stock, where you basically have like this network trying to understand the scene. Then you have this thing called point slam. Again, this is really similar to nice slam, but then now rather than having like these tiny grids of nerves, you kind of have like a neural point cloud, which basically a 3D point cloud, where each point also has some feature, and now you can you train this network to kind of take these features and then give you the actual image which you care about. And I would say in more in terms of the classical sense, we also compare against this method called elastic fusion, where the idea is to basically use these things called surfills along with ICP-based registration, basically. And then so you can think of surfills almost as like a flat way of representing a 3D Gaussian. So they're basically just like a 2D Gaussian in some sense, but then they're in 3D. So yeah. And then the other ones we compare to are basically OpSlam and DroidSlam. So these are like one of the most famous, or I was like most popularly used classical SLAM systems, where you basically have an feature-based front end to do the camera tracking, and then you have more of the classical-based optimization to kind of get the geometry itself. So yeah, so in terms of tracking performance, when we kind of compare all of the methods in a SLAM setup, on replica, we can observe that the 3D Gaussian based representation actually provides 2 times better performance compared to nerve based representations, mainly nice slam and point slam, and it also beats classical or like learning based representation, like I guess like classical systems like droid slam in the same setup essentially. And then on TUM RGB-D, again, we show significant boosts over volumetric methods, and we also show that for the first time, I guess like a nerve-based or I guess like a radiance field-based method actually beats an explicit method despite like noisy depth, which is typically present in RGB-D cameras. And then on ScanNet, we find that this JSON actually has a lot of high motion blur and depth noise. So we find that all methods tend to have very, I would say, mediocre performance here. And then lastly, on the benchmark which we construct, ScanNet++, we find that both the prior explicit SLAM systems and also both the nerve-based SLAM systems actually have a failure of camera tracking, while our method actually has about 1 centimeter of tracking error, which is insanely good. And let's probably take a closer look at this one. So when we actually looked into why classical methods were kind of failing in this setup, here you can see that it's really hard. Like you have mostly textureless white walls, and it's really hard to kind of pick up interesting features in this scenario. And then now, for example, over here you can see that our OpSlam kind of fails to get good features consistently, so it keeps reinitializing itself. So you kind of end up with this like meaningless camera tracking trajectory and also 3D map. So this is like one of the key drawbacks of like these explicit methods or like the traditional methods to do SLAM. And then on the other hand, we kind of show that our method actually provides sub-centimeter camera tracking, which is like I would say very exciting in some sense. So then I guess what about the actual fidelity of the representation itself? As in like how do the images actually look? Do they look even pretty in some sense? So in this setup, what we find is when we compare this to nerve-based methods, we actually have competitive or better performance across the board, which is again another exciting factor, kind of showing that you're not really trading off any kind of quality in some sense. And then when we take a closer look, essentially on let's say multiple data sets, for example, over here on replica, we find that when you use 3D Gaussians compared to nerves, 3D Gaussians tend to actually capture a lot of these fine details, which are typically missing in nerve-based methods. For example, on the top part, you actually can see it's like the clock over there doesn't really have a lot of detail. It actually is like a blurry smudge. While in our method, SplaTAM, you can actually see that we can really capture these fine details with these 3D Gaussian-based representations. And then likewise, we also find, and then I guess like another drawback of these nerve-based SLAM methods is that you actually need to use ground truth depth to render from new views. So for example, let's say in an AR setup, now once I reconstruct the scene, or for example, let's say I have some geometry, and now from a new camera pose, I want to kind of render this scene. These methods actually require you to know the depth from that new camera pose to also enable you to actually render. While in SplaTAM, we don't need all of this stuff. Like we can actually render the scene from any kind of camera pose without any kind of privileged information, while still having very high fidelity. For example, here you can see the window blinds actually have a lot of detail compared to prior methods. And likewise on Scar++, we also find that we have very high performance compared to prior methods. For example, over here, qualitatively, you can observe that the prior state-of-the-art point slam kind of fails to provide good reconstructions, even though we give it even ground truth poses, as we actually take the ground truth poses from the data set and give it to the method. Even then, it kind of struggles to kind of reconstruct the scene with high fidelity, while on the other hand, we actually provide very high fidelity, which is again a very cool, exciting factor, kind of showing you that the 3D Gaussian representation is really robust. Now let's take a look at a scene reconstruction from Scanner++. Overall, as you can see here, we basically observe that our method has about 0.6 centimeters ATE RMSE, and while SOTA baselines actually fail on this trajectory. And then also we kind of show that both from training views and also from novel views, we actually have very high fidelity in terms of reconstruction quality, which is a nice thing. And I guess the nice benefit of these 3D Gaussians is that because they're based on rasterization, you can actually use this representation at speeds up to 400 FPS, which is insane when you think about like VR applications. So here are some like qualitative visualizations of our method on like some other different scenes. For example, on the left side, it's like a slam visualization, while on the right side is like the rendering of this scene from a novel camera pose, basically. And lastly, I guess in the slam world, you also do care a lot about like how fast you can actually reconstruct this scene online. So we also do a bit of a benchmarking on an RTX 3080 Ti, and we compare this to again prior nerve-based slam methods, and we find that I guess there are a few bottlenecks right now in our implementation, but then overall with the current implementation we have about 2 FPS online speed essentially. And then lastly, we kind of also ablate a lot of like our design choices regarding like the use of the silhouette mask, and then how important like different classes are. But when you kind of do the optimization, and also I guess the Gaussian properties itself. But again, I'm probably going to skip across this slide and not really go into a lot of detail here. And lastly, in addition, I guess, is that when we open sourced our code, we also released this demo where you could take your iPhone and actually record 3D Gaussian reconstructions with your iPhone. And for example, over here, I'm actually showing you a few results from our office, and also from one of my friend's apartments in the bottom right corner, essentially, which is a very cool thing. And likewise, here are some other, I would say, interesting captures which we tried, where, for example, over here on the left side, we tried to capture one of my friends. And then I guess on the right side and on the bottom, these are actually people who've tried out our method on Twitter, and then they've actually shared these reconstructions with us, which is, again, kind of exciting, kind of showing that this method actually works in the wild too. And then, and yeah, you actually can even try out these own reconstructions on your phone or laptop. So please feel free to scan these QR codes or go to these websites. You can actually take a look at 2 hour SplaTAM reconstructions. And then the other thing is, if you actually open up this on your phone, you can actually interactively move around this scene as you move your phone, which is very cool. I'll probably give you a minute to kind of, I guess, look at the scene if you're interested. But yeah, I guess overall, I guess through this talk, I've hopefully convinced you guys that 3D Gaussians are really like an exciting representation to enable SLAM. in these three ways. Why do we need them in the first place, and then how to do actually SLAM with the 3D Gaussians, and also like what's the outcome of this. Why should someone care about this? And then I guess lastly, before I kind of conclude, I also want to kind of give a shout out to a lot of concurrent work which has come out in this space, kind of showing that there is like a lot of unique ways to do SLAM with these 3D Gaussians. So for example, all of these papers came out like I would say a 1 month span, and then it's really cool kind of showing that like multiple people kind of think the same about this representation in terms of SLAM. For example, there was this paper called GSLAM, where they use coarse-to-fine tracking to kind of select the Gaussians, while there's like this paper from Andrew Davison's group called Gaussian Splatting SLAM, where again they kind of use this median depth-based installation of Gaussians. And then there's another method called PhotoSLAM, where they actually couple like prior classical SLAM methods like OrbSLAM with Gaussian mapping. And then there's CalMap-free 3DGS, where you basically couple like monocular depth estimation methods with 3DGS. And then another one, the last one I kind of want to mention is Gaussian SLAM, where again you're kind of coupling prior traditional SLAM methods with like submaps of Gaussians. And I guess the very interesting thing, I guess the really cool thing is basically there's like a survey paper after a few months which kind of compared all of these methods in the same setting. And we kind of found that our method actually has 1.5 times better camera tracking compared to the closest Gaussian splatting based SLAM method. And likewise, I guess, in the context of this talk, I mainly kind of showed you applications in terms of, let's say, SLAM, and then also, I would say, nerves in some sense. But then, I guess, yeah, more from a view synthesis perspective. But the really cool thing is these Gaussian representations also have very cool applications in a robotics framework, basically. And particularly if you want to really compress these representations or again, use them in an embedded setup. There's a lot of very cool work from CMU where we've kind of shown that you can actually use these representations in a nice way. And then, I guess back in February this year, we were really excited to kind of see that, a lot of people using our code. We had like about 1,000 stars and 100 folks on GitHub, and then all the code is public and anyone can actually try out our method with their own collected data. But then obviously there are a few exciting follow-ups which we're kind of pursuing right now, where I guess one of them basically is to kind of increase the scale of the reconstruction, which you actually can do. For example, really expand these things to like large scale scenes like mining sites and other things, so that they're actually useful for real world applications. Then the other one, basically, I would say, is more like a research kind of thing, where like you're trying to like use features also to kind of improve the representation. Likewise, again, there's another similar one where basically you want to kind of use like neural networks or like deep networks to kind of train your model. And the last one essentially is, I would say, how do you select which next view or next camera you should select to kind of improve your reconstruction in some sense, which is again an active problem in some sense. So finally, to recap, I would say the key takeaway home message I want to kind of give you is, I guess, generally for people who are interested in camera tracking and SLAM, I kind of showed you in this talk why 3D Gaussians are the apt representation for dense SLAM. And then in general, for people outside the SLAM community, I think the key takeaway I really want to highlight today is basically the 3D Gaussian representation actually has very nice, elegant properties. For example, like the silhouette rendering, which are widely applicable to many other applications in general. So it's not just for SLAM, but like the 3D Gaussian representation actually is very cool in terms of like its applicability to other problems also. And lastly, before I conclude, I would like to thank my co-authors and friends who actually helped me with a lot of parts of this work and also this talk. And then with that, I would like to conclude. Thank you so much for coming to the talk today. And I would highly recommend checking out our website and code. And yeah, I'm happy to take any questions.
Thank you very much, Nikhil. That's for me really answered a lot of my questions. And I think the last, first of all, when we announced this webinar, we put the URL to your repo in there so people can also find that in their inbox and other places, because it's really one of the huge benefits, I think, of working in an open community like the research community is people want to share their code. They want other people to try it and, and improve it if they can.
Yeah.
So, but, this brings me to like, if people are not in the research community, which the AR for Enterprise Alliance is composed primarily of people who are trying to apply this in their daily business. They could be providers of technologies that are providing products or services, software or hardware, or they could be customers, those people who are buying those technologies and putting them to use and deploying them, implementing them into their workplace. And so at the end of your talk, you started to say, the general audience, like, who cares? Why does it matter?
Yeah.
I think I just want to jam with you, riff a little bit on that. Why does it matter? And I think that if you're a provider of technologies, then you need to check out these new methods to do SLAM. Yes, you may need to understand what 3D Gaussian splatting, at least superficially, is. And you will get that background from this talk. But I think the key take-home message for the providers is you better get your feet wet here now, because if you don't, you're going to be bypassed like super fast. And if you're just entering the field of augmented reality and you need ways of doing SLAM, don't look for other directions. This one is so big and so promising. You need to choose some of the SLAM, some of the 3D Gaussian splatting techniques. What you've also shown is you can mix and match, which is another thing that I think providers need to really think about, how to mix and match how they do SLAM. So let me be quiet and see if can you bring this all the way into the enterprise use cases? Like, why does it matter to a customer?
Yeah, sure. I can totally. I think I think you kind of make a very great point. As in, like, I think the other thing is, I think over here I kind of showed as like one versus the other kind of setup. But then, as you totally mentioned, this thing can actually be used with other complementary techniques too. So which is like another exciting thing where, like, example, you could use traditional tracking systems with 3D Gaussians to do the mapping, which is another exciting paradigm, I would say. I would say in terms of applications, yeah, I think this is actually very cool. For example, even in our lab, or like, I guess, like other projects I've worked on, people have always been looking for like a representation to kind of, for example, let's say if you take the example of construction site inspection, right? For example, in Pittsburgh, inspecting these bridges and all of these things are like a very important task for the city over here. And then there's a lot of projects, both from, let's say, the government and also from other companies, where they're interested in actually autonomously inspecting these different, the quality of these different structures. And then it kind of becomes important that, ideally you'd not want a human to carefully capture all of these, should I walk through this entire tunnel and like capture every corner of this? But then you actually want some automated technique to do this, right? Like you just probably just capture it in a casual way. And then if the technique is actually really good, hopefully you can capture at a very high fidelity. And I think the cool thing is, I think with more and more research, we kind of get into a phase where we can actually automate all of this stuff, where, like, for example, like these kind of 3D Gaussian representations can give you the accuracy needed to kind of achieve.
Yeah, I think to take it to the augmented reality space, if I know you're part of a robotics department, that's going to be autonomous systems, cars, other things like that. That's where your DNA is. We're thinking the human has this on their face,
Yeah.
initially they're going to have it in a tablet, but they're going to have it in their head-worn display, and they are going to have more precision about tracking the real world, so that when there is some discrepancy detected, the human that's standing there gets a signal and says immediately, what I'm looking at is not according to plan, or what I'm looking at is damaged, or there's it can communicate with the user immediately, because of the simultaneous localization and mapping. The other thing that I've been working on a long time is visual positioning systems.
Mm-hmm.
So the visual positioning system needs to take the reality that's coming in the camera feed and compare it to something else that's been tracked before. And the delta, the distance between what was mapped and what I'm seeing as a user is getting smaller and smaller. So I think the precision with which our systems can localize the user in real space is going to go up. But mainly, I think this being able to recognize the table, recognize the machine that the person is using right away, and then overlay on that in high detail, high precision. Can all this run on a device, on one device? Tell us about the power requirements and the computational requirements. We didn't get into that at all, I noticed.
Yeah. So I think that was, so right now, yes, I agree. So I think definitely even for this work, the whole computational requirement and also the speed of the method itself was like a very, very big focus. And I think, and I guess if you actually think about other companies too, operating in the VR and AR space, for example, like Meta, they do really care a lot about like making these things accessible, or like where you can actually use them in the headsets for real time tracking, or like I would say, as you said, overlay in an augmented reality setup. So I would say definitely there are promising trends here. There are a few papers which have come out in the recent days, kind of showing that it is actually possible to use these representations. It is actually possible to use these representations to run real time. Obviously, you'd probably, if you would really want to run these on hardware, I guess one of the problems basically is you have to kind of cater and engineer the representation itself to be efficient, and you have to really cut corners in some places basically. And I think right now that part actually requires some amount of know-how, as in you need some amount of expertise to kind of know, okay, these are things I can maybe trade off for like more speed. But I think eventually what's going to happen is, as more and more research papers come out, and then people start like really developing these open source repositories. For example, there's like this repository from UC Berkeley called Splat, which always kind of incorporates all of the latest new papers into like this common code base, so like anyone can always keep using this code base to kind of develop Gaussian Splatting technology. So I think that the cool thing is these kind of things can actually help us adopt these things for real world applications, and both for real time stuff. So yeah.
Fantastic. Yeah, great. I think that's the time we have for the questions and the discussion. This has really been valuable. You can trust me to follow up with you and your team members. As you said, it's not just one person. You're a great speaker. You had a fantastic ability to communicate to us what's important, how this is done. But I want to come back and say, this is a very big, active community of researchers with different approaches, a lot of overlap, like you said, the G-Splat, that's a really, community. It's a community of people. So thank you, Nikhil. This is really great. Thank you on behalf of the AR for Enterprise Alliance, and hope you have a good rest of your day.
Yeah, thank you so much. Yeah. Bye.
Bye.